There we go. Okay, so precipitation reactions are really, really easy. The only thing that makes precipitation reactions challenging is if you don't know how to name things. If you don't know your nomenclature, it's going to be really hard. Okay. Can anybody, just before we start, can anybody tell me what a precipitate, which is what a precipitation reaction is? What's a precipitate? What is that?
An insoluble mass that is the result of a reaction in an aqueous solution with something that doesn't dissolve in that solvent.
Okay, that's perfect. Can you maybe say that a little bit simpler for people that don't understand what insoluble means in aqueous, just layman's terms?
It's something that doesn't dissolve in water, although water is not the only solvent.
Perfect, exactly. It's something that doesn't dissolve. So it's a solid, right? Something that does not dissolve when in water. So usually what happens is in a precipitation reaction, you have these two things that you start out as liquids, right? You have these two clear, they're usually clear because a lot of the ionic salts are clear, but not all of them. But anyway, you have these two clear liquids, and then all of a sudden you mix them together and now a solid forms. So that solid that's forming is the insoluble part of the reaction. That insoluble part is called the precipitate. That's why these are precipitation reactions, because when you mix these two clear liquids, or not, doesn't have to be clear, but these two liquids, you mix them together, they react and a solid forms, so a precipitate forms. That's called the precipitation reaction. There's another name for these precipitation reactions. They're also called double displacement reactions. Why are they called double? Well, actually, before I even ask that, what does displacement mean?
To move
Right.
something out of the way.
You switch, exactly. And that's exactly what happens. The precipitation reactions are also called double displacement because the two partners, right, like the two reactants that you start with, all they do is basically switch partners. So that those are the products. You know the reactants, if you can successfully switch the partners, and make the correct products, then that's it. So what you should expect in a precipitation type question is I'm going to give you stuff in words. Okay, so I'm going to tell you this compound in words reacts with this compound in words. Can you tell me what happens? So I'm not going to tell you the products, so you have to form the products. But if you understand the whole concept about switching partners, then it's easy. The hard part is, okay, I know which partner switches with who, but do you know how to put them together? The products, do you know how to, or even the reactants, do you know how to put them together properly with their proper charges and the proper formula? That's why this is difficult. If you do not know your nomenclature, you can't even start this problem. Okay, but before we even do a precipitation reaction example, I am going to show you, there's a chart, and I think that's the first slide. Hold on. Yeah, there's this chart. Okay, so this chart is in your book, in your book, like the real book. But this is called the solubility chart. So what does this chart tell you? It tells you things that are soluble in water, okay, at this particular temperature, but that doesn't really matter for these problems. So, for example, the reason I show you is because this chart is a little bit, it's counterintuitive. If you notice this chart, it like splits it in half, right? So anything on the top of the red line tells you that whatever is on the left, like see compounds containing alkali metals. So all these alkali metals are always soluble, right? So everything on the left is soluble, but then you have things that are certain exceptions. The exceptions are on the right. But if you notice, you go down to the bottom part of the chart, it kind of flips it on you. So now on the left, you'll have what's typically insoluble, typically carbonates, chromates, sulfides, all those things are insoluble, except the exceptions are on the right hand side, on the right column. So it kind of flips it. I show you this because it's not super easy. If you've never seen it, it's not super easy to understand. So I want to show it to you so you know how to read it, because that's that's really important. What you're gonna have this chart in your exam, so you need to know how to read it, okay? One thing I will say about that is that you will have this chart, but it's not gonna be exactly the same. And let me show you how yours, let me skip through this stuff first and show you how yours is gonna look. So see this chart? This chart is exactly the same, but what's different about this chart?
It doesn't have the formulas.
Right, so in the other one, remember it said sulfates, but then it showed you the example of what a sulfate is. Obviously, this is the one that's gonna be on your exam, so you're not gonna have that. So you need to know what they are. That's why this is difficult, okay? So let's go back and actually do this simple question. And this question, these little practice exercises down here is just to make sure that you guys know how to read the chart and be able to give me an answer. So classify the following ionic compounds as soluble or insoluble, okay? So what's the first one called?
Copper sulfide.
It's not just copper sulfide, you're missing something.
Copper monosulfide.
When do you put
Copper.
mono in an ionic compound?
Oh, sorry,
That's
that's not.
definitely not it. What? Sorry, go ahead.
Copper 2 sulfide?
Yes, copper 2 sulfide. Why do you put the 2?
Because sulfide has a -2 charge and
Nope.
charge?
Oh, well, you weren't done. Sorry. Go ahead. What were you going to say?
Because their charges cancel each other out. Like sulfide.
Right. But that's always for an ionic compound. Why is this one called copper 2 sulfide and not just copper sulfide? Why do you have a Roman numeral?
Copper is a transition metal.
Thank you. So it is copper 2 sulfide, not because the sulfur balances out. It's because copper is a transition metal. It's in the block. So whenever you have a transition metal, you got to tell me the charge with the Roman numeral. So that's why you say copper 2 sulfide. Okay, so cool. Copper 2 sulfide. So is copper 2 sulfide insoluble or soluble?
Insoluble?
Insoluble. Why? Where'd you see that?
The insoluble compounds?
You see right here? That's what you looked at?
Yes.
Okay, so sulfides are typically insoluble, except when it's a sulfide that's containing an alkali metal and the ammonium ion, right? So those are the only two exceptions when you're looking at sulfides. Everybody understand that? Engagement class, thank you.
Yes.
Engagement, thank you. So what's the next one called? How about somebody else talk? Okay, I'm gonna start picking on people. Drew, what's B called?
I don't know. I think it
Ooh, your Wi-Fi is going cray cray. I'm gonna pick someone else. Sorry, Drew. Kezia, what about you? What is it called? Kezia, hello.
I'm coming.
Where are you going? Are you searching for the answer?
No. Is it calcium hydroxide?
Uh-huh, it is. Okay, so can you tell me if calcium hydroxide is soluble or insoluble?
Would it be insoluble?
Why?
Because it's listed hydroxides are.
Okay, and what are the exceptions for hydroxides?
If it contains an alkali ion, metal ion, and barium, is it?
Uh-huh, and is calcium not an alkali metal?
Wait. Yes.
Is it?
Wait. No, it's an earth metal. It's an earth metal.
It's an alkali earth metal, and that's why it is insoluble. Okay, good job. Isaiah, what about the third one?
Is it zinc 2 nitrate?
Okay, you don't say zinc 2 nitrate. Why do you not do the Roman numeral for zinc? Does anybody know that? Does anybody know that you do not do the Roman numeral for zinc?
Because it's already a full octet.
No. Good guess, but no. Anybody? Why do we give Roman numerals?
For transition metals?
Right, but why? Why do we give them Roman numerals?
I'm sorry, you cut off. What'd you say?
Why do we give them Roman numerals?
To give them their specific charge.
Because they change charges, right? So if zinc does not have, you do not have to put a Roman numeral, what does that tell you?
Its charge doesn't change?
Exactly. So even though it's in the transition metal block, it does not transition. It's like it's a special dude. It's a special guy. So it's an anomaly. So you don't provide the Roman numeral for zinc, and the other one is silver. Silver is another one that's in the block, in the transition block, but doesn't transition. Does anybody know what the charge is for silver? Always? Hello? Anybody?
1.
1. Yes, that is correct. So you have to remember that. So if you get a compound that has one of these transition metals that don't transition, don't put a Roman numeral because you're going to look kind of dumb. They're going to be like, really? So this is called zinc nitrate. Whoever said that, I don't remember who I called on, but that was correct. But not zinc 2 nitrate. So zinc nitrate, is this insoluble or soluble?
Is this for anybody?
Yes, go ahead.
Insoluble.
Insoluble?
It's soluble.
It's soluble. Okay, yes. So it dissolves. It dissociates in water. Yes. Why? Because if you look right here, it has nitrates. Nitrates, as a matter of fact, look at this entire little section here. It has no exceptions, right? So that's actually quite important because when you start doing these precipitation reactions, you should try to remember, or at least keep in the back of your mind, the things that are always soluble. Excuse me, always soluble. It doesn't matter who they're connected to, they're always gonna break up. For example, the nitrate. Nitrate is very, very common, right? So nitrates, anytime you see a nitrate, you know that you have to put the aqueous symbol, right? So that's what's soluble. When you see something that's soluble, it has this symbol, aqueous. If it's not soluble, it'll have this symbol, the S, because that means it's a solid, okay? So we're starting to use these states now. These are called the states. So if you see a nitrate, it's always going to be aqueous. And look what else is always soluble. What always is soluble are those, what are these guys? These are all the alkali metals. So the entire first column, except, yeah, rubidium too. The first column are always soluble. So you don't even have to, I know it doesn't make like, oh, well, who cares? I'm just going to look at the chart for 1 second. But you see, you'll save yourself a bunch of time, seconds here and there, if you know, oh, it's a nitrate aqueous, oh, that's a alkali metal aqueous. So you really only have to look at the chart for the one thing that you don't know. It will help you to save time. Okay, does everyone understand how to read this chart? Because if we are, we're going to move on.
Yes.
Yes.
Okay.
I have a
So,
question.
go ahead. What's up?
I was gonna ask, so what happens if it has G in there? Would it still be the same or no?
What happens if it has what in there?
G, like with the aqueous and solid, is that also the same for gases?
No. So those are gases, and we're not going to deal with gases yet. So don't worry about gases. Okay. we'll do that next chapter. So we're really only concerned right now with things that are aqueous or solid. We'll actually also see Ls. Ls means liquid, which is basically talking about water. That we'll see in this chapter at the end. But really for precipitation reactions, it's either aqueous or solid. That's what you're looking for. Okay. So precipitation reactions, really, really simple. All right, so we've talked about that. That's what a precipitate is. So this is an example, and obviously I'm giving you the equation, the reaction, but remember, when this actually happens, I'm gonna give it to you in words. So I would say lead 2 nitrate reacts with sodium iodide. And then then the question becomes, okay, what happens? What products? Tell me what happens when I react those two things together. So it is your responsibility to make the rest of it and do everything on your own. So the trick here is that you guys understand ionic compounds. You do. We've done them since day one, right? So you know that in an ionic compound, there's a positive portion and a negative portion. And if you know that all they're doing is switching partners, then this should be really, really easy if you know your nomenclature. So for example, what's the positive portion of the first reactant? Who's positive? Is it the lead or is it the nitrate in the first reactant?
Lead.
It's lead, right? So then that means that this guy is the negative portion. If you do the same thing to the second compound, the sodium is the positive, it's the metal. Metals are always positive. And iodine is the negative part. So look at the products. Let's say that the products weren't there, but that, you know, all you got to do is say, well, okay, so this positive is going to switch partners and now go with the other negative. And if you notice, look what happens. That's exactly what happens. The lead switches the partner, goes with iodine. Okay, and then obviously the other thing, the sodium goes with the other partner, which is nitrate. That's all you're doing in a precipitation reaction. You're switching partners. The trick is to make sure you put these things correctly, the molecular formulas correctly together, okay? So the first step of a precipitation reaction is actually writing out the regular equation, this reaction. It's called actually the molecular reaction. It's just the first normal reaction. I'm not going to tell you to balance it. So you would need, once you put them together, right? Once you make your products and you make your reactants, you got to balance it. Got to make sure it's balanced. And then you would go to the chart and figure out what states to put, right? So is it a solid or is it aqueous? And how do you know that? You know that by looking at the chart. So obviously this example, I've given it to you already because I just want to kind of show you what it is. But do you understand the process thus far?
Yes.
Yeah, okay,
Yes.
so just basically you got to make a reaction. You got to make it. You got to know your stuff, your compounds, and you got to make the products, and you got to balance, and then you got to figure out if they're soluble or insoluble. Okay, this first reaction, like I said, oh yeah, so this would be the precipitate that's formed. So how do you know it's a precipitation reaction? You have two aqueous solutions reacting together to form a solid. That's how you know it's a precipitation reaction. That's it, super simple. But anyway, this is called the molecular equation. It's just the first normal equation. The next step, there's 3 steps to a precipitation reaction that you need to do. The next step that you need to do is you need to break everybody apart that can be broken apart. What do I mean by that? These are ionic compounds, right? So you know, and if it tells you right here, if it's aqueous, you know that if you put that lead nitrate solution in water, the ions are gonna split, they're gonna break apart. So that's what the next part is split up everybody that can actually be split up. So I'm gonna just show you what it would look like. But if you see here, look how everybody is broken up into ions, which is why this equation is called the ionic equation, right? So you break in the second part, it's called the ionic, and you break everybody that you can into ions. So what do I mean that you can break up? Well, for example, look at the solid, right? The solid doesn't break up. So that dude stays together. But everybody else, because they're aqueous, can be broken up. So this would be the next step, is you break up everybody into their respective ions and realize that everybody has a charge because they're ions. If you don't put their charge, the correct charge, it's wrong, okay? And then also notice that, well, let me not say that yet, but do you understand that part? The next equation would be the ionic equation, which means break everybody that can be broken up into ions. You understand that?
Yes.
Okay.
Yes.
So the whole point of this is to figure out who is actually reacting at the end. So you have, the way that you figure that out is going through these steps. So you have your first molecular equation. The second one you break up into ions, whoever can be broken up. And if you notice, there's certain things on both sides of these equations that are the same exact thing. Can someone tell me what those things are?
2Na plus.
Right, so if you see here, there's a 2Na plus right here on the left, and there's also a 2Na plus right here on the right. What else is the same on both sides?
The nitrate.
The nitrate, exactly. So at this point, what you would do is sort of treat it like an equation. If you have this, like a mathematical equation, if you have the same exact things on either side, they cancel. So you literally would go, oh, 2NO3, 2NO3, cancel, cancel. 2Na, 2Na, cancel, cancel. What are you left with?
The precipitate?
Well, the dude, the people that actually make the precipitate. So your precipitate that you knew from the beginning was lead iodide, lead 2 iodide. And what you should be left with at the end should be the people that are making the lead 2 iodide. That is always the case for precipitation reactions. The only people that should be left, so let me show you part 3. Part 3, well, let me cancel, 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 cancel. Here's the last part. This is called the net ionic equation. The only people that are left at the last part, the part 3, is the people who actually make the solid. That is the whole point of you doing this entire process. You have to make the molecular equation, so you got to put everybody together, balance it, figure out who's a solid, who's not, blah, blah, blah. Break everybody up for part 2 that can be broken up, and everybody else that is not involved in making that actual solid should cancel. If they don't, you did something wrong. You balanced it wrong, your formulas are wrong, you maybe looked at the chart wrong, something went wrong. So that's kind of like your check, okay? So these guys that are not used, right, are called what? Does anybody know?
Spectator ions.
They're called spectator ions. And I say this every class, every year, and it's kind of corny, but I like to kind of make an analogy, like these guys here, the spectator ions, they're kind of like the people that are designated drivers at a party, okay? Like they don't actually have fun. They don't actually go in and drink and do whatever. No, they just actually, all they're doing is taking the actual people that are going to party and do whatever to the party. So these are the people that are actually partying, right? The people who are making the solid, those are the only people that are actually reacting. That's the only thing that's happening in that reaction, is the lead is coming together with the iodine and making lead 2 iodide. Everybody else is just still floating around in the solution as ions. They're not doing anything, right? They're just like sitting there, they're spectating, they're watching. They're watching the people that are actually having fun and making something new, making a solid. So does that make sense?
Yes.
Does that make sense?
Yes.
Go ahead.
I feel like I'm gonna ask a slow question that you probably already explained, but I'm gonna hear it again anyway. So, okay, how am I going? Everything, I just noticed that everything that was liquid canceled out and then the solid stayed. So does that go for like every other equation that we might possibly do? Or
they're not liquids, they're aqueous solutions. Is that what you mean? The people that are aqueous?
Yes, that's what I meant.
Yes, so the people that are aqueous are the people that can split up, okay? But if you notice, PB splits up on the left, but it doesn't split up on the right. I guess, I don't know, I'm not really sure what your question was, but does that answer it? Can you ask it again?
I was saying that the aqueous solutions cancel each other out, but like, so it
But
was
not
a,
all of them.
but not all.
of them, right? Because, for example, the lead is part of an aqueous solution, but lead ends up at the end.
So what happens if all of them can be split up together?
Then you have no reaction. That's actually a great question, because that's one of the examples I have at the end of class. That can happen. What if they're all aqueous, right? What if you do your reaction? That's like a trick question I could give you. What if you make your reaction and you look at the chart and all of them end up being aqueous? So that means that you put them all together and they're all gonna just float around in the solution. Nothing's gonna happen. So no reaction. So nobody cancels. Okay, or everybody cancels. Yeah, everybody cancels. So yeah, well, that can happen, and that was a good question. Anybody else?
Hear me?
What did you say, Camille?
You can hear me, right?
Yep, I can hear you.
Okay, so like piggybacking off of her question, like in that case, would you have a precipitate?
Can you answer your own question? Camille,
Oh, no.
are you kidding me?
Just
Listen to
making
what you're
sure,
asking.
because like,
Oh my God. Listen to what
it
you're
could have been
asking.
wrong.
Listen to what you're asking. If everything is aqueous, is there going to be a solid? Is there going to be a precipitate?
No.
No, because everything is aqueous. So no, the answer to that is no. There's no solid. If everything is aqueous, then you don't have a precipitation reaction because you don't have a precipitate. Okay? Any other questions? Okay, so let's try. Oh, this is actually, these slides are a long time ago I made them. So this is just like the steps if you guys want to, have steps. This is the steps that you would do to do a precipitation type problem, right? Write the balanced molecular equation, check the chart. Actually, that should be in there. Check the chart to see who's aqueous, who's not, balance it. And then part 2, write the ionic equation, split up everybody that can be split up, cancel the spectator ions, and get your net ionic equation. So that's exactly what we just talked about. So let's try one. Okay, so this is a typical thing. I'm gonna put you down. This is a typical type of problem, right? So everything in words. So predict what happens when a potassium phosphate solution is mixed with a calcium nitrate solution. So potassium phosphate, can someone tell me what that is?
K3.
Okay, what?
3.
Okay, but tell me the whole thing.
K3PO.
K3PO what?
4.
Okay, good job. K3PO4. Why is there a 3 here? Because phosphate is PO4 3 minus. Okay, and why is there nothing on the other side of this phosphate? Because K has a +1, because it's an alkali metal. Good job. Okay, so we're just gonna go ahead and write everything down first before we go look at the chart. So what is calcium nitrate? Somebody else. Oh my God, guys, come on, bro.
CaNO32.
So I didn't hear the first part. What did you say?
I said CaNO32.
NO32. And 2, why? Why'd you put that 2 at the other side?
Because calcium has a +2 charge.
Perfect. Okay, so let's go ahead and make the products. Remember, they're just switching partners. So tell me who you think the first product would be.
The potassium.
Well, okay, but it's not just potassium. Tell me.
Agree.
Say again.
Sorry. So it wouldn't be the potassium that goes first.
I'm asking the first product, so it's a compound. It's not just
What
an
is-
element.
Product. Sorry.
Potassium nitrate to go first.
Sorry, say it one more time. I thought I heard you say it. Did you say potassium?
Potassium nitrate goes first.
Yes, ma'am. That is the exact name, correct name. Can you tell me what the formula is for that?
KNO3.
Good job. KNO3. Okay, so that's the first one. So then who's the second guy?
Calcium phosphate.
Okay, that's the name. Great. What's the formula?
Okay, so it's gonna be Ca3, PO42.
Good job. That's it. So that's calcium phosphate. Now, the next step would be to go look at this chart, right? And figure out who has an AQ and who doesn't have an AQ. But remember, start thinking about the ones that are always soluble. It'll help you. Remember, do you guys see anything here that we talked about that is always soluble?
The nitrates.
That's right, the nitrates. So go ahead and just go put AQ, because you know these are going to be soluble. Exactly. Is there
I have a
anything
question.
else that you know is always soluble? Remember?
Is it the potassiums?
Yes. Why? Why is it the potassium?
Because it's in the first
Column.
group.
Exactly. It's an alkali metal. So all the alkali metals, anything that's connected to an alkali is going to split up. So it's always going to see, it's always going to be aqueous. So you see, you saved yourself some time. Now you only have to look at the chart for one thing, which is the calcium phosphate. So let's do it. There's your chart. Can someone tell me if it's soluble or insoluble?
It's insoluble.
It's insoluble. And even though it has an exception, right? That exception doesn't apply.
No.
No. Okay. So that means that this guy then is, hold on, let me move you guys. Where are you? There. So that means that this guy is then your solid. Great. What's the next step?
Balance the equation.
Yes, ma'am. Can someone balance it? Help me balance it, please.
The 3 in front of the K.
Okay, you're gonna speak like a scientist now. In front of what K? In front of what compound? Because I know what you're talking about. But
Potassium nitrate.
potassium nitrate. Okay, good job. Okay, so you have a 3 in front of there. What else?
Wait,
Wait.
would the Bond's equation be, you would put a 2 in front of the calcium nitrate?
No, you guys are getting, let's start over. It's not that difficult.
Can you hear me?
Yeah, I can hear you, Kezia. No, you would not put a 2 in front of the calcium nitrate.
Okay.
Come on, you guys.
Would you put it in front of the potassium phosphate?
A 6 between, I'm sorry, what? In front of the potassium phosphate?
2.
A 2, okay, okay. Then that gives you how many potassiums?
6.
Right, so what do you have to put in front of the potassium nitrate?
A 6.
Okay, so what else do I do?
You put a 3.
Okay, in front of the calcium nitrate. Yes, that is, now it's balanced. If you check, everything is balanced. 3 calciums, 3 calciums, 2 phosphates, 2 phosphates. Everything's balanced. Okay, now we're good to go. Now we move on to the ionic equation. In this step, you break everybody up that's aqueous, that you can break up, right? So someone tell me, what do I write? Okay, we're not gonna get to finish if you guys don't talk.
I'm still working on it, but would you put K plus?
Okay, but how many Ks? You got to transfer the coefficients too. Like everything has to be balanced.
Oh, okay. Hold that thought.
6K plus.
Okay, so you would put 6K plus. That's the first one. Good job. Next.
I have to go in order.
Couldn't hear you. Say it again.
Do I have to go in order? Like, can I
Yes.
say?
Yes, we read from left to right, Kennedy. So go in order, please.
2 phosphate minus
2 phosphate minus 1.
Minus 3.
Okay, so 2 PO4 3 minus. Okay, next.
Plus 3 calcium.
3 calcium what?
Plus 2.
Okay, so the reason I keep harping on that is because remember, this is the ionic equation. You have to have ions, okay? If you don't, it's wrong. So you've got to tell me the charge, always. So yes, correct, 3Ca2 plus. Okay, next.
And then 6 nitrate minus.
Minus what?
Minus 1.
Okay, so 6NO3 minus 1 yields. Okay, good job. How about somebody else? Come on, guys. Somebody else. Let's go.
Six K plus.
Thank you very much. 6K plus. Next, go. Keep going.
6NO3 minus.
Good job. And then next.
And then everything else stays the same.
Yeah, so you don't split that other one up, right? Because it's a solid. So Ca3, PO4 stays exactly the same. There's your solid. Okay, good job. This is your ionic equation, and it's also balanced. So it's important. You guys have to realize that all these little steps matter, right? Because let's, for example, well, let me not even go into that, but everything is still balanced and will always be balanced. And you, even from the beginning, when we made this reaction, the first one, you should have already known who's going to be at the end. The guy that's the solid is calcium and phosphate. So that means that everybody else besides calcium and phosphate should cancel. So what cancels here?
Potassium.
So 6K.
Nitrate and not phosphate, but potassium and nitrate.
That's right, which look what's left. And I'm not going to rewrite it, but look what's left. 2PO4, 3Ca2 plus goes to calcium phosphate. There's 3 calciums on the left. There's 3 calciums on the right. There's 2 phosphates on the right. There's 2 phosphates on the left. Everything is always balanced. Everything is still balanced. So that's why the whole balancing matters. And the whole, like, you got to bring the coefficients down matters, because if not, it won't cancel. So that's it. I mean, that is literally how you do a precipitation reaction. The hardest part, I mean, I know you guys understand the steps. The steps are not hard. What's hard is making sure you put these formulas together correctly. That's why nomenclature is so important since day one. So you really have to get to know these. Any other questions? Do you have any questions? Because I want to do some more. We still have time. Any questions on this?
No.
Okay. You sure? Everybody else? Okay. Okay, so there's a chart. Let's do some other ones. So, oh Lord, hold on. Okay, same thing, right? All these precipitation reactions are exactly the same type of question. You just have to make the products and make you know, whatever. But what will occur when a solution of lead 2 nitrate is mixed with a solution of potassium iodide? So here we go. What is lead 2 nitrate?
PbNO3 2.
PbNO3 2. Perfect. What's potassium iodide? Is that what it is? Yes, potassium iodide.
Is it just Ki?
It is just Ki. Good job. Okay, what are the products?
K2NO3.
That's incorrect. Yep. That's incorrect. Why would you say K2NO3? Why'd you say K? Where's the 2 come from?
I could be wrong. Is the nitrate, does it have a charge of 2 or no? Or -2?
Definitely not. Absolutely not. It does not.
The lead PBI 2
PBI2. Okay, that's correct.
plus KNO3.
Okay, that's correct. Okay, so first, right off the bat, can you guys tell me what's aqueous here?
PbNO3.
Okay, I heard PBNO, what? Sorry, what's aqueous here?
The nitrates and the potassium.
Thank you. The nitrates, I think I heard someone say it, but I don't know, I was confused. So the nitrates, so both nitrates on both sides are aqueous, and you also said the potassium. So the potassium for the same reason that the other problem was, because it's an alkali metal. So you see how you save yourself time here. You don't have to look at the chart for 4 people, you only look at the chart for 1 person. And before we look at the chart, I do want to kind of like harp on, I don't remember who was it you, Cherish, that said K2NO3? Was that you?
I don't think so.
You don't think so? Okay, well, whoever said it, see how easy, you know, realize how easy that can be to mess up the whole thing, right? Because if you, let's say if you do K2NO3, right? Like that is going to screw up your balancing. That's going to screw up maybe potentially making the wrong product or whatever it is. You know, maybe what if potassium nitrate was a reactant? That'll potentially screw up making an incorrect product. So it's like a domino effect. So you have to know the nomenclature, because if you do, it's like you're done. It's going to be so difficult, and you're going to be super frustrated. So I can't stress it enough. You guys have to know your nomenclature. So, okay, the only thing that we're using the chart for is that PBI2. So is it soluble or insoluble?
Soluble?
Someone said soluble? I couldn't hear. So can you say that again, please?
Soluble?
Soluble. Okay, so why do you say it's soluble?
Because I'm sorry, I just had a brain fart.
Okay.
Could you repeat the question, please? Sorry. For the one that you wanted me to answer for, what was soluble?
Yes, PBI2. That's the only one we're looking for. Is it soluble or insoluble?
Okay. It's soluble. Was it because of the iodine?
Where do you see iodine being soluble here?
Is it soluble because of the exceptions?
It's insoluble, right?
Okay, so you
It's
guys, that's why I showed you the first question and asked you if you know how to read the chart, right? So it is insoluble. Why?
Oh,
Why, Camille?
it's soluble because the lead is a halide. It's an exception.
Okay, lead is not a halide. Lead is not a halide. What is a halide?
a halogen ion.
Okay, what is a halogen? What column is the halogen?
The one right before the noble gases.
Correct. So the seventh column. So who there in that compound is the halogen?
Iodide.
Iodine, exactly. So because you're looking for this, so Cherish, you kept saying lead. Lead is the exception. Lead is not the halide, right? So halides are chlorine, fluorine, bromine, iodine. Those are halides. So there is a section for halides, but they are typically soluble. The only exceptions they have is if they're connected with a silver, a mercury, or a lead, which in this case, it's a lead. So that's why that's your solid. Does everybody understand how to read the chart?
Yes.
Are you sure? Because that was
Yes.
confusing. Okay. So yes, so that guy is your solid. And then it's the same, right? So did we balance this? No, we didn't. So is it balanced? Nope, it's not. So can someone balance it for me?
You put a 2 in front of the Ki on the left side.
Okay.
And put a 2 in front of the potassium nitrate on the right side.
Okay, and now before we even start it, who should cancel by the end of this process?
The potassium and the nitrates.
Okay, does someone disagree? Does someone not understand? Oh my God. Okay. Ionic equation. Somebody tell me what to write.
Lead or Pb 2 plus
Okay.
2 NO3 minus 1 plus plus 1 and plus 2I minus 1.
Okay, next.
The lead iodide wouldn't dissociate because it's the precipitate.
Thank you. Next.
Two K plus, and then 2 NO3 minus.
Okay, what cancels? Like you said, Justin, the Ks and the NO3s, Ks and the NO3s. What are you left with? The guy that makes a solid. 2 PB, 2 and 2 Is, and your solid, your thing on the right is PB, 2 Is. Perfect, done. Okay, we have 2 minutes. I want to do the other one. Zinc sulfate, what is it?
It's ZnSO4, and you don't have to write the, well, never mind.
Zinc, ZnSO4. Okay, what is magnesium chloride?
MgCl2.
Good job. MgCl2. Good job, both of you. What are some products?
Magnesium sulfate,
Okay, can you give me the formula for that?
MgSO4,
Okay, and then the other product?
zinc chloride, it would be ZnCl2.
Okay, good job. So anything here that you can write off the bat, maybe say it's aqueous? Not that I know of actually, that I remember. So zinc sulfate, let's look at these sulfates. Zinc sulfate, is that soluble or insoluble?
It's soluble.
Okay, does everybody agree, or is it just Justin and me in the class?
I agree.
Okay, so okay, so aqueous. What about the magnesium chloride?
It's soluble because it's a halide.
Because it's a halide and it's not connected to any of those people, silver, mercury, or lead. Okay, what about the magnesium sulfate?
It's insoluble because, oh wait,
It's insoluble.
It doesn't dissolve? Why? Where do you see that?
it's soluble. Yeah, I changed my answer. Because it's a sulfate, not a sulfate. Yes, it is. It's a sulfate. That's why it's soluble.
Okay, final answer?
Soluble.
Okay, soluble. Thank you very much. It is soluble. What about zinc chloride?
It's soluble
Okay,
because
so
it's a
here you,
halide.
exactly, because it's a halide. So here you have an example where all of them are aqueous. So that means we didn't actually balance it, but it is balanced, isn't it? Zinc, chloride. Yeah, we didn't balance it, but it is balanced. Here's an example. Everything is aqueous, and you have no precipitate. So therefore, this is not a precipitation reaction. So therefore, if you mix these two guys together, all that's going to happen is all these ions are going to split up, and they're just going to be floating around in solution. So nothing's going to happen. Okay, so that is the whole thing for precipitation reactions. I mean, that's it. It's really simple. Hard part, you got to know your nomenclature. You don't, you're screwed, unfortunately. So tomorrow, well, today we have a thing, if you guys want to come to it, at 7 o'clock. But tomorrow we're doing redox, okay? So that means that you have to learn how to do oxidation states. Terry left and he didn't hear what he has to do for tomorrow, but okay. You have to learn how to do oxidation states. You have to know how to do half reactions. So, I mean, it's not news to you. This was, you knew that we were going to cover this, but that's what we're going to cover tomorrow. And we're probably going to cover it on Monday too, because it's a lot and it's a little tricky. So we're going to take 2 days. And then after that, it's dilutions and titrations and we're done. So do you guys have any questions?
Yes, I have a question. So in the case of a reaction like the last one where there is no precipitate, would you want us to still write the net ionic equation to prove that there is no precipitate?
No, you can state it. I thought I was sharing. You can just state everything is aqueous, no reaction. That's it.
Okay.
Yeah, that's fine. Any other questions?
Are there any quick tutorials that we need to do? I checked before, there weren't none, but
Nope.
okay.
They take me a long time to make those, and I'm really tired of making them. So I don't know if you're going to have any more. Maybe towards the end for electronic configurations, I'll do one. But for a little bit, I'm going to take a break on them. Any other questions? Okay, so redox tomorrow. All right, I will see you there. All right, guys, if that's it, thank you so much. I'll see you later if you guys come to the study session.
Thank you.
Thank you. See ya. Bye.